Welcome to Monochemistry. Today we're going to look at the molecular structure of acids and how that helps determine the strength of the acids. Now remember, there's two major groups of acids that we're going to look at here. There's oxoacids, and there's also another group called binary acids, but more specifically we're going to look at the hydrohalic acids, which are basically, as you can see here, the group 17 nonmetals attached to a hydrogen. Those are the halogens, so hydrohalic acids comes from that. Now, from this list, you should be able to identify both the strong and the weak acids. You don't necessarily know why, though. Why is one acid stronger than the other than the fact, as we've talked about in previous lessons, that strong acids are able to ionize or dissociate at a much higher level than weak acids. So in this lesson, we're going to learn about how the molecular structure of the acid leads to its ability to dissociate or ionize in water. Let's start with the hydrohalic acids. Hydrohalic acids, as I already mentioned, are hydrogens bonded to group 17 ions, or elements, I should say. Recall that strong acids, as I just mentioned, dissociate nearly or up to 100%. So what makes a hydrohalic acid strong and what makes it weak? Well, for binary acids in the same group of the periodic table, as it mentions down here, the HA bond strength decreases as the size of the A, which is the anion, increases down the group. So as you can see here, hydrogen fluoride, hydrofluoric acid, is much weaker than HCl, which is weaker than HBr, which is weaker than HI. So as you go down the group, the acid strength increases. Now the question is why? And here's why. The bond energy, or the amount of energy it takes to separate the H from the A, decreases as you go down a group. HF takes 568.2 kilojoules per mole to separate, whereas HI only takes 298.3 kilojoules per mole to separate. Notice HF is weak and HI is strong. This is from page 687 of the Chang textbook. This table 15.6, it's from page 686 of the Chang textbook. The question is why? Why does the bond... This is related to lattice energy. If you recall lattice energy, there are two factors that determine the lattice energy of a substance. One of them is the strength of the bond between the positives and the negatives. And the other one is the size of the atoms. So let's have a quick look at the size of these atoms and see if we can't determine why HF has the strongest bond and therefore is the weakest acid. Alright, so here we have a picture of the atomic radius and the ionic radius. We're only going to look at the atomic radius. And here you see fluorine's atomic radius, chlorine, bromine, and iodine. And as you can see, the atomic radius increases as you go down the group. Now hydrogen would be up here, and it would have a relatively small atomic radius. Recall that we spoke about, with respect to lattice energy, that molecules that can form really strong bonds tend to be the ones that can get close together. So if we have hydrogen up here, which is a really small atomic radius, and fluorine here, which also has a very small atomic radius, they can get really close together, and therefore it makes it very hard to pull them apart. Also recall that when a substance is dissolved in water, water will completely surround that substance. In the case of ionic substances, like technically these ones would be, it's able to separate them. So the H plus and the F minus would be separated from one another. But if that bond is very strong, the water won't be able to do that. So all of these, water is able to break apart because their bond energies, or the amount of energy it takes to break them apart, is very low. But the amount of energy it takes to break apart HF is very high, and therefore it doesn't ionize or dissociate in water, which makes it very weak. Let's move on to other binary. Another trend you may see is in other binary acids. Technically, all of these things here are acids whether or not we always think of them as acids, they technically can be with the Bronsted-Lowry definition. Okay, but as you can see, as you go across the period from C to F, notice what happens. You get an increase. Okay? Before I said the stronger the bond, the harder the harder it is for the water to separate them. But in these cases, you have very non-polar molecules moving into more polar molecules. So the acidity actually increases with electronegativity across the periodic table. So from left to right, acidity increases with electronegativity. In other words, water is not going to be able to separate this into H plus and CH3 minus. It's not going to be able to separate this into H plus and NH2 minus. It's not going to be able to separate this into H plus and OH minus. And it's going to be able to, more so, separate this one into H plus and F minus. And that's due to the polarizability of these molecules and the ability of water to be able to separate them. Okay, so as you go across a period, the acidity increases with increasing electronegativity. However, as you go down a period, the acidity, down a group, the acidity also increases because it's easier to separate the substances from each other, the atoms in a molecule from each other. Let's move on to oxoacids. Here's a list of oxoacids. Again, you should be able to tell which ones of these are weak and which ones are strong. Now I'm going to give you 3 general rules of thumb to follow. Okay? Alright, so in an acid like these, the more electronegative this is, the easier it is for O and H to form their slightly negative and slightly positive charges. Okay? So the more electronegative this guy is right here, the more likely this is to happen, and the more likely this is to be able to separate it in water. Okay, so the more electronegative this is, the more acidic the substance is. Okay, now Z represents all of these things you see here. Okay, so the more electronegative this whole group is, right, it has to be the whole group. The more electronegative it is, circle these here for you, the more electronegative that is, the more likely the thing is to be acidic. Okay, that's the first rule. Now, how can you tell? How can you tell which ones are going to be more acidic? Very quickly. This is rule number 2. The number of oxygens has to be 2 or more than the number of hydrogens. The number of oxygens in the acid has to be 2 or more higher than the number of hydrogens. That's one really quick way to look at a substance and say, yes, that's going to be acidic, or no, or sorry, yes, that's going to be a strong acid versus no, that's going to be a weak acid. That's rule number 2. Rule number 3 also involves Z, right? The oxidation state of the central atom in Z. The oxidation state of the central atom, and the higher the oxidation state in the central atom of Z, the more acidic the substance is. Okay, and those all go back to this idea of the more polarizable this is, the more likely it is to form a delta negative and delta plus, the more easily water is able to separate the hydrogen from the substance. And that leads, of course, to an increase in the H plus concentration, which of course lowers the pH. That, in a nutshell, is how you use the molecular structure to determine the acid strength. Here are my sources for this. Make sure you bring your questions to class.